Okay, so welcome to part 2 of the gas basics or kinetic molecular theory notes. So we're going to start off on the bottom of page 2 talking about Dalton's law of partial pressures. So this is probably a review and it's pretty intuitive. Basically what Dalton's law says is that the total pressure of a mixture of gases is the sum of the pressures of all the gases that are in that mixture. Okay? So if I have a mixture of hydrogen gas and helium gas, okay, the total pressure of that mixture of gases is going to be equal to the pressure of the hydrogen plus the pressure of the helium. Okay, makes sense? This is because gases behave so similarly to each other that really their molar masses and that are so negligible compared to the overall space that we can just treat them as pretty similar. Okay, all we need to know is the mole fraction of the individual gases. Basically, what fraction of the mixture is that gas? So if you were looking for the mole fraction of A, you would take the moles of A divided by the total number of moles of the gas, the sum of all the gases that make it up. Okay, so we can also use this in relation to the total pressure. So the partial pressure of gas A is always going to be equal to the mole fraction, so what fraction of the mixture is that mole, times the total pressure. Okay, so the pressure and the number of moles are very much the same thing. Okay, total pressure depends on the moles in total. Partial pressure depends on the moles of each individual gas. Okay, and the total pressure will always be equal to the sum of those partial pressures, no matter what gas we're talking about. So let's do a hard example problem that takes into consideration some stuff that you'll see later, and then you guys will solve out some basic applications of Dalton's law. Okay, so mixtures of helium and oxygen are used in scuba diving tanks to help prevent the bends. The bends is how scuba divers get sick if they raise up too fast. For a particular dive, 46 liters of helium at 25 degrees Celsius and 1.0 atmospheres. Okay, so we have that gas. Okay, and then we also have that being added to 12 liters of oxygen, which is also at 25 degrees Celsius and 1 atmosphere. Okay, so there we have those gases. Okay, liters, two gas, okay, oxygen diatomic. Okay, and they are pumped into a tank. Okay, so they're pumped into a tank with a volume of 5.0 liters. Okay, so both of these gases are going into that tank. We expect the pressure to go up dramatically because you're taking a big volume of the gas at one pressure and shoving it into a smaller area. Okay, so we expect the pressure to go up. This is getting into gas laws, which is actually our second set of notes, but just trust me for right now. Okay, so we're going to use one of the gas laws. Again, this is something from our next set of notes, so don't worry about it if it doesn't look familiar, but it might from regular chemistry class. There is a thing that the pressure times the volume equals the pressure times the volume. Okay, so both our gases were originally at 1 atmosphere. Okay, so that's going to be our P1. Okay, the original volume of them was the total volume, or 46 plus 12, which gives me 58 liters. Okay, so that is our initial volume. And then we know our volume ends up being 5 liters. So we can use that to figure out the pressure. So P1, like I said, both of them were at 1 atmosphere. V1, they had a volume of 58 liters, equals P2, which is what we don't know, times V2. We know they got compressed to a volume of 5.0 liters. Okay, so let's solve it out. We have 58 liter times atmospheres equals 5.0 liters times P2. I don't know why I moved those around, just have it, divide by 5 liters. Oops, I crossed out the wrong thing. My brain's totally working on this lovely Monday morning. Okay, divide it. And I get 11.6. The liter units cancel out the liter units, so I'm left with atmospheres, which is what I expect for a pressure. So my P2 equals 11.6. Okay, now that's the pressure in that 5-liter tank. And this was the sum of both gases. So is that going to be my partial pressures or my total pressures? Okay, yes, that is my total pressure. Okay, that is my PT, or I use that for P total. Okay, now we need to find the partial pressures. And remember, partial pressures are just the fraction. And yes, it's supposed to be in moles, but we have it in liters, and we know that for every liter of a gas, it's 22.4. And it doesn't matter, so we can just use that as the fraction. Okay, so I'm going to go ahead and erase this work. Make sure you have it down. Pause the video if you need to. But I'm going to go ahead and erase this. Okay, now let's talk about the partial pressures. To get the partial pressure of the oxygen gas, I have to take the fraction that is the oxygen gas. So the fraction that is oxygen is 12 out of the total, 58. Okay, again, that's my 12 liters of oxygen divided by my total liters of gas. Okay, the fractions you can do in any units. I know I said they were moles, but you can do them in any units because for gases, it doesn't matter. Okay, multiplied by the total pressure, which is 11.6. Okay, when we do that, we get that the partial pressure of oxygen is 2.4. Okay, oh, and I need to put my units. 2.4 atmospheres. Okay, so a couple different ways that we can get our partial pressure of helium. We can do the same thing, or we know that the total pressure is going to equal the pressure of the oxygen plus the pressure of the helium. So we can also just subtract. So to get my pressure of helium, I'm just going to take the total pressure, 11.6, and subtract out the partial pressure of the oxygen. So 11.6 divided by 2.4, and I get, oopsie, sorry, I don't know how to math. 11.6 minus 2.4, and I get 92. Okay, so 9.2 atmospheres is my partial pressure of helium. Okay, and again, you could check that with the mole fraction. If I did the mole fraction, it would be 46 out of 58 times 11.6, and you get the same answer, 9.2. Okay, cool? Okay, cool. So that was a hard problem. That took a lot of things into consideration, but let's try just a basic, pure Dalton's Law problem. Okay, so again, make sure you have all this down before I erase it in 3, 2, 1. And I want you guys to try this one. The partial pressure of oxygen was observed to be 156 torr in a total atmospheric pressure, so P total, of 743 torr. And they want to know the mole fraction of O2. So what is the fraction that is O2? Go ahead and see if you can figure it out. Did you guys get 0.210? Hopefully you did. So in order to find it, remember that the partial pressure of any gas is the fraction that is that gas divided by the total. So to get the mole fraction is just, hey, what's the O2? Hey, what's the total? And you just divide it. So you end up with 156 divided by 473, which gives you 0.2099, which we can round to 0.210 in order to keep track of our sig figs. Mole fractions do not have units, so don't worry about that. Okay, cool? Okay, cool. let's talk about kinetic molecular theory. So, kinetic molecular theory is a model of a gas that assumes that a gas is an ideal gas. What we mean by that is that our particles are in constant random motion. Hey, when they collide to each other, it's perfectly elastic, which means they bounce off of each other. Think billiard balls, not balls of clay. Okay? The volume of the actual particles, negligible. Okay? They're so small compared to the spaces between them, we can ignore it. And the average kinetic energy of the molecules is its Kelvin temperature. So those are the 4 postulates of kinetic molecular theory. Super great. Some of the problems with it is that it neglects any intermolecular forces between the gas particles, which normally isn't a big deal until you get into certain situations. Okay, so what might cause there to actually be forces between gas particles? Would it be under a high pressure situation or a low pressure situation? Well, if it's low pressure, that means they're not running into things that often. So it must be only under those high pressure situations that they run into each other. So the higher the pressure and the lower the temperature, the more a gas deviates from ideal gas behavior. Okay, because once you raise the temperature, they're moving around so fast, they're spread out, they don't really interact much. But high pressure and low temperature, those are both things that could cause a gas to turn into a liquid. Okay, think about gas water condensating on the walls of your glass because it's cold water in there. Okay, it gets cold, so it calms down. So when you do things like raise the pressure or lower the temperature, the gas starts to get more toward liquids, and thus it deviates from an ideal gas more. Okay, so those are some of the problems with kinetic molecular theory. Okay. But let's talk about these gas particles and how they're moving. Okay, remember, temperature is just the average kinetic energy. And the AP chemistry test loves to show you graphs of this energy, which, remember, is related to speed. Okay, do you guys remember that kinetic energy is the energy of motion? Okay, so K for kinetic energy is 1/2 the mass times the velocity squared. So when we're talking about temperature, we're talking about energy, which means we're talking about how fast those particles are moving. Okay, couple things, and here's a graph of fraction of molecules versus molecular speed. At any temperature, some gas particles are going to be moving fast, and some are going to be moving slow. At any temperature, okay? It's not just because it's a certain temperature, they're all moving slowly. No, it's an average, okay? Some are moving fast, some are moving slow, just like people in the hallways, okay? As temperature increases, the distribution of the speed gets wider. So notice the O2 gas at 1,000 degrees covers a much wider range. There are more particles moving at different speeds, okay? But the area beneath the graph doesn't change because, it's the fraction of molecules. You only have a certain number of molecules, okay? The area beneath the curve, what it is related to typically is the number of gas particles, okay? So when you raise the temperature, you're not going to move the graph over. You're just going to level it out, okay? And as the temperature increases, what you're going to do is you're just going to increase the gas particles over here that are moving faster. Okay? So that's what this graph shows you. Oxygen 25 degrees Celsius, most of them are moving at about 400 meters per second, where oxygen at 1,000 degrees Celsius, most of them are moving up here like 800 to 1,000 meters per second. And it just widens out. Okay? So we can rearrange the equation to find the average speed of a molecule. That's called Maxwell's equation. This is a V, so V RMS means root mean speed, okay? But it's the square root of, this is a derivation of the gas law where R is constant, T is temperature, and then M is the molar mass, okay? You don't need to be able to solve out these equations, okay? What you do need to know is that, hey, heavier molecules, they're gonna move slower, which makes sense. Heavier objects tend to move slower. Okay, so molecules that have a high molar mass, versus molecules with a low molar mass, they're going to be moving slower. The faster, at a certain temperature, the ones with more molar mass are going to be moving faster. The ones, start over. The ones with high molar mass are going to be moving slower at the same temperature versus smaller molecules, which can move faster at that temperature. And hey, if you raise the temperature, they're going to go faster. Okay, more energy, faster molecules. So they like to show you guys graphs like this. This shows all of the molecular speeds at a certain temperature. I think this is at standard temperature, which is 0 degrees Celsius. Okay, so this is all at the same temperature. Now, notice who here is moving the fastest. Okay, which molecules have molecules moving the fastest? Well, it's this orange line, which is H2. Okay, H2, you know the molar mass of H2 is 2 hydrogens, so that's 2.02, which means hydrogen must be the lightest molecule, which is weird because you think it's 2 atoms, but helium has a mass of 4.00. Yep, 4.00. So it's actually a bigger particle than hydrogen. Okay. At the given temperature, what is the average speed of these He molecules? Okay, to get the average, you just go to where the graph is the highest and go straight down for there. So it's somewhere in between 10 times 10 to the second, which is 1,000 meters per second, and 15 times 10 to the second. So I'm going to guesstimate it's probably somewhere around 11 times 10 to the second meters per second. I think somewhere around there. But you're just looking at where that highest point is. Okay? Because you'll notice they're all pretty normal distributions-ish. Okay, cool? Okay, cool. That's it for those notes.